Hello again. This is module 4, the first video on coverage-based structural white box testing, where we go into more details following up on module 3. I'm sorry for the fuss and delays, but I've had a series of problems. So I had a hard disk crash and I've been ill. Still not fully well, but I'm on pills, medication. So hopefully my headache won't affect too much. Let's get going. So we talked about white box, black box testing last time, gave an overview to testing levels and so on. Now let's dive into maybe the most concrete type of testing, coverage-based or structural testing. So what is this? Well, it's fairly simple, as you know. We discussed it a little bit last time. We focus on executing all parts of the program. So we create test cases in order to hit all parts of a program. Depending on how we define hit or covering parts, what are the parts that we consider, we get different types of coverage-based testing or structural testing. So the main reference for the work is the source code itself, and we are going to try to go through it and ensure that we have executed it in many different ways and covered the structure of the code. Okay, so that's where it comes from. Coverage, covering the structure. So, but it's also called only coverage-based testing. But coverage-based testing could be coverage of a model, some other type of model than what we're going to focus on here. So structural testing or white box testing is more commonly used. So goals are twofold, of course, to find good tests in a systematic way. And that's a side effect of that. When we run them, we, of course, as in all testing, we can find problems, bugs, defects. Another one is to know when to stop testing. So this is a big problem. How much testing should we do? When are we ready? And so on. And coverage-based criteria they are the main way that people do this, especially in industry, but also in standards in different industries and so on. So these are sort of the two main goals. And how complete our testing is in this paradigm is based on the structure of the code. So once we decide which parts of the code will we focus on, we decide which part of this code structure is our focus, and then we basically count how many percentage of the structure that we focus on that we have covered. So the most simple example is statement coverage, where we count how many of the statements, so basically lines in the source code, depending on how you define statements in your programming language, but let's say line coverage, then the simplest form of statement coverage. Every line of the source code, non-empty line, should have been executed at least once. Then we would have 100% coverage. If we only cover 60 of the statements for a total of 100, of course, then we would have 60% statement or line coverage. And then, of course, so the technique of structural testing is we decide which test cases to run based on the structure of the code. Of course, you all know, we discussed last time, that to complete the test case, we would need the oracle. We would need to know what is the correct output for this test case, right? So structural testing doesn't really help us with the output correctness. That we have to take from our experience or from a written down requirement or specification in some way. So two different elements to it there. And this is simple. So you have all seen probably these types of code flow graphs. So this is a graph that we can construct from a typical program. And this is sort of the quintessential way, the typical way that you do this. So you analyze the source code into some kind of code flow graph. And here we have one example. And then you take your test cases and you compare how will this code flow graph be used during the execution of these test cases. So if you see here in test case 1, if the input is 0 for the argument A and 1 for the argument B, we will come in from the top into the node N0, and we will look at A, is it larger than, equal, or less than B? And in this case, A is 0 and B is 1, so we will go from the node N0 to the node N1 for this test case. And then we have covered the nodes 1 and 0 in this case when we run test case 1. When we run test case 2, A is now 0, B is also 0. So we will come from the top into N0, and we will then go to node 3, and then from there on to node 4. So we have taken the path through the program control flow graph from N0 to N3 to N4. So this is the path of this test case execution, and the path for the previous execution is N0 and then N1. So in this case, you can see that we have not visited node 2, so we don't have complete coverage on any of the criteria, actually. So, of course, when we do this translation, of course, there are tools for this, but this is more to give you a conceptual understanding. Most of you have already seen this, of course. Then it depends on how does the structure of the source, how is the source code actual? Then we need to translate it in different ways. Here you see a typical if clause without an else. So here we come in from the top, and there you have the decision if x is less than y, so it's a condition and a decision actually. If x is less than 1 and less than y, we go to node N1, and there that's a node called a basic block that represents several statements in the program. So a basic block is every node in a control flow graph represents one basic block, but each basic block can have one or more statements of the program, because if there is no exit from that basic block, it's merged into one node of the graph. On the other hand, if we come in to N0 and x is actually larger than or equal to y, then we will go to N2, which is called the junction node after the if statement here, which is then merging the flows, the two different paths that we can take there. And then, of course, for for loops and other constructs, it might be more complex, but you can see that it's quite easy in principle. So you have an example with a for loop, and then you have to make sure that you don't forget the update of the loop variable and so on. But you can see that there are easy ways to translate most programming languages to these types of control flow graphs. And based on the control flow graph, you can calculate a number of different coverage criteria, and they are used. And depending on the industry, the company you are at, you select sort of a different level of coverage or structural testing that you do, and then these type of graphs and this type of analysis can help you go further. So let's look at it. So we're talking about dynamic verification and validation techniques. We're talking about, and that's testing often. We're talking about the structure-based testing, and there are 5 main types. Statement, decision, and condition we'll go through today in this video, and then in the next video we'll cover path and data flow. Actually, there is a link missing there to the path one. Sorry about that. Okay, so let's jump into statement coverage, the simplest. You already covered it in theory, but it's also called C0 test, but these are a little bit confusing, these terms, so they are not used so much any longer. We use the real name. And statement coverage basically takes the graph and looks at, have we visited every node, right? Because if every node is a basic block, which means it's either one statement or a series of statements from which you cannot exit, then we can be sure that if we have visited every node in the control flow graph, we have visited every statement. So there must then be the case that for every statement of the program, there must exist at least one test case in the group of test cases that you're running that cover this specific statement. And so the coverage measurement here is called statement coverage, of course, and it's just the number of executed statements over the total number of statements in the program. And most open source libraries actually have systems that check this continuously. I will do probably a short video later in the course and show you how this can be done in one language, how it looks, and so on. Here we can see that we can cover this specific graph by only 2 test cases. This is, yeah, you can follow it through here, but the green one, test case 1, takes the rightmost path and goes through N0, N1, because it has A larger than B, so it goes from the decision node N1 to N3, and then from N3 onto the junction node in N4, and then again there is an A is larger than B, so it goes to node 5 and there to the junction node N6 where this piece of code ends. And then the next test case takes the leftmost node, but in the first decision, but takes the same rightmost path in the second decision. But as you can see, all nodes have been covered, so statement coverage will be 100%. So this is the most used coverage criteria there is. This is the most used structural testing technique. And many companies aim for 100% statement coverage, which means basically you have no dead code. Dead code being code which is not executed by any of the test cases. But so this is very common. It's something that many companies aim for, but it's well known since a long time that it's not a good to detect defects because it's a very basic coverage criteria, a very basic type of testing. But still, it's better than not covering all statements, right? So depending on where you are in your maturity as a testing company and engineer, this can be a good thing to strive for, but it's been shown that it's probably not cost efficient to only go for this and push for the last percentage if you have a very large system. But some other reasons why this is not so good is that we don't really look at the data dependencies themselves. So we only look at the structure of the code as sort of a dead artifact. So we don't really have a better understanding of why are we taking different paths in the execution. And thus we can miss important dependencies between data. Another problem is that every statement is of equal importance. So this is not the case. For example, you can imagine when you actually run a piece of code, some parts of it will be used much more often than others. So the actual editing in Microsoft Word is used all the time, while printing is less common actually. So the actual parts of the code which handles everything that has to do with the editing in some sense is more important because it's going to be used much more of the time. The problem with statement coverage is that every statement is counted once. So this doesn't take the importance or complexity or something like that into account. Loops, it's enough to execute a loop once, so you don't need to actually check many of the conditions and what can go on in loops. If you've just been through the loop once, you have ensured 100% statement coverage, so you can imagine that there are many complex computations going on that we haven't really tested. And then a quite common problem that was found in safety critical software early on in the 60s and 70s already was that when things went bad, when there was a serious failure, defects were often down to we hadn't tested combinations of different decisions that are taken in if statements and in for loops and while loops and so on. So the combination of different decisions that are taken is very important, and statement coverage doesn't look at that. You only need to take paths so that you cover each basic block or each node in the graph once. But these were four of the downsides, but it can help to find dead code. It's the most commonly used criterion, so it's very important for you to have a good understanding of it. Here is one quite recent and now research paper that got a lot of attention in the industry and also in the research community, of course, where they studied 31,000, they generated 31,000 test suites for 5 systems. And they are not super large, but in total they amount to 700,000 lines of source code, these 5 systems. And they generated test suites, and they measured what kind of coverage they got for each suite, and then they looked at, then they introduced faults in the software. So they changed the software so that it was faulty, and then they evaluated if all these 31,000 different test suites actually could find the bugs they had introduced. And the interesting thing is down here, we found that there is a low to moderate correlation between coverage, so they studied several of them, and the effectiveness. So with effectiveness, they mean finding these bugs that were introduced, so they knew that there were bugs in there. So they basically said that the coverage depends more on the size of the test case. So when you control for that, if you take a test suite of the same size, one that has a higher coverage does not really give you much more in terms of finding defects. So this was a large empirical study that showed what many had seen in practice. And you can go on and you see that the stronger forms of coverage do not provide greater insight into the effectiveness of the suite. Of course, this paper has been debated a lot, so you cannot claim. So there is some benefit in increasing coverage. I think the truth here is that at some point there's sort of the diminishing returns in just going for coverage, and you need to upgrade to something more stronger. So decision coverage is another form and a stronger form of coverage. So here you look at the graph, and we have the same graph as you saw in the previous statement coverage example. And we look at not the nodes that we considered in statement coverage, but we look at the edges, right? So the difference here is that test case 2 has been changed. So instead of the red line here, test case 2, instead of going from node 4 to node 5, it goes straight from node 4 to node 6, right? And what this does is that since test case 1 in green has already covered node 5, and that's a wasted test case in a sense, and it's actually better to take these 2 test cases, because then you get both 100% statement coverage and 100% decision coverage, because we have covered all the edges in this graph, right? So this was the change here, and this means that there is a path when you execute the test cases where every edge has been taken. So this means that every decision in an if statement, else statement, for loop, while loop, and so on has to be true and false at least once in the test suite. So this is a higher level, but in that study they showed that okay, it didn't provide much benefit, but it is a benefit, because you can see here that these 2 test cases actually gives us both 100% statement and 100% decision coverage. So this is often considered the minimum test criteria, right? Because you're covering both the nodes and the edges. But in practice, most people still go for statement coverage. I think mainly because tools have focused on this, and they, in some sense, it's easier to code tools, so they measure statement coverage. But decision coverage is also used. The problem it has is that it's not well adapted to loops, and it's not good for testing combination of branches. We are only checking that we covered every edge once. We are not looking at the combinations of different edges, right? So we're still not getting a complete coverage of the whole type, all the types of execution there can be. So combinations are not covered fully. And then nested decisions, combined decisions are not properly tested. So if you have a very complex um, condition in a if statement, you only look at the whole thing being true once and false once, right? You don't look at the individual parts. And if we have put individual parts in this decision, they are probably important, so we need to test them. But this type of coverage doesn't help with that, so that's why there are even better ones. And they are called condition coverages. So we build up from statement to decision to condition. So condition coverage, now we go in detail and look at the decisions. And here we see a decision statement, the whole thing, the example here. So we take a decision based on this complex condition of logical conditions. So there are atomic conditions here, and they are the x larger than 1. That's the first atomic condition. The next one is u equals 0, the middle one, the second one. And the third atomic condition is v equals 0, right? So we have 3 atomic conditions, and then we see that the atomic condition 2 and 3 are combined with an OR operator. So now that's one combined or complex condition, and this combined one is then with the AND operator combined with the first atomic condition. So in total there's a hierarchy here of levels. At the lowest level we have atoms, and then they are combined through logic operators. C1 test decision coverage is just that the whole thing, the decision itself, has to evaluate true and false. But as we saw before, that doesn't cover all the combinations here. So then there are stronger forms of condition coverage called C2 and C3. And there we also go in and look at the atomic conditions in different ways. So there are different forms. Simple condition coverage. Then we only focus on the atoms, right? So we only in the previous case we had 3 atomic conditions, and we ensure that we have test cases so that each of these atoms have been true and false, right? This is still not complete, of course, but we can go further. We do minimum multiple condition coverage. So now the terms and names are getting complex. So now we look at also the partial conditions in the hierarchy, right? Also including the root. So they have to be true and false. But this can lead to quite a few combinations, of course. So the modified condition coverage, MCDC, is something that you actually see used in industry. And there you check the atomic terms, clauses, and you check that they actually have an effect on the root decision, right? So you don't focus too much on the in-between conditions. You look at the atomic conditions and the main thing. And you look at, have the atomic conditions affected the main decision, right? So modified condition coverage, MCDC, is a more practical form. It's better than simple condition coverage, but it doesn't reach the multiple decision coverage, which is to cover all combinations. So let's look at the simple example here. Here we have 4 variables that can be true or false. So we have simplified it a little bit. This means there are 16 different ways that they can take on true and false, from number 1 being all false to number 16 being all true. So if we have the complex condition on the right here, A or B, ANDed with C or D, right? So we have 4 atomic conditions, and we have 2 intermediate but complex decisions and 1 root complex decision. So simple condition coverage means that we need to only select, for example, test case 6, because there we see that A has been false, B has been true, C has been false, and D has been true. So now we only need to select the flip of that, test case number 11, because there you see that now all of them have their inverse. So in total, they have both, if we execute test case 6 and test case 11, all of the atomic conditions have taken on both true and false. So we fulfill simple condition coverage, but you can see that there are 14 other possible states of the world which we have not considered. So minimum multiple condition coverage. Now we add that all the partial decisions need to be taken. Yeah, so here you see actually that it's the same as simple, but we do it also, we have to ensure that all of the intermediate and the root conditions have also taken on true and false. So this is actually it's enough also with 2 cases, but we are considering more things, so we are more constrained. We actually have to select these probably. I haven't checked that, but if we select 1 and 16, then all of the atoms and the intermediate conditions have taken on true and false, so we have fulfilled minimum multiple condition coverage. But actually MCDC is even stronger, because it ensures that all of the atoms have had an effect on the root, on the main decision. So the next step would be to consider also that the intermediate conditions had an effect, but this is rarely used because it becomes too many test cases then. But modified condition coverage called MCDC, and this, if you will work in Volvo embedded systems types of companies and so on, this is something that you will hear, because in some of their standards they have to use MCDC. Here, every condition must be true and false at least once, so atomic conditions. And every decision, so the top level decision has to be true and false at least once. And then we have to show that every atomic condition and decision should affect the outcome. So this is required in many safety critical domains, such as aerospace by NASA and so on. So what can we do? If we select out of these 8 here, it's a smaller example. A, B, and C are the atomic conditions, and the root top level is A or B or C. Then we first select 4. Then we see that A is true, and it means that the root decision is going to be true. But B and C are false, so they don't affect the root here. So we have to now find another one. So we take number 6, and there we cover the F for also A, which is good. And then we have a true for B. So B is now affecting the root, right? And then we select 7, and in the same way we now cover the false for B. And we also have C now being true, and it was false before, so now C is affecting the root decision. But we're not done, because all of these 3 test cases, 4, 6, and 7, lead to the root condition being true. So we also need to select one where it's false. So we take all of them false, A, B, and C, and then the root condition will be false. So 4 test cases are selected under MCDC here. And this is often in practice if you have very complex decision conditions. MCDCs, even that is fairly complex. Of course, multiple decision coverage means that you need to cover all combinations, and this explodes in the number of ways. And especially if you have several decisions being taken in your program, this can lead to already many test executions without even considering the combinations, right? Okay, so that was it for this first part. So fairly straightforward, but it's good to really go through it and think through it. Maybe I messed up a little bit how clear I was here, but you can also check SCTP book. They have good descriptions of this, and I hope that these examples help you out. And then in the next video, we'll discuss path, data flow testing, and discuss a little bit how these things can be used as test criteria. Thank you.